All right, so let's talk a little bit about this comparison of stats methods blog post. Maybe we should just start with why you wrote it in the first place.
We get a lot of questions from folks about should we use this method versus that method? Do you think Bayesian methodology gives us better results? We are considering sequential testing, but we are worried about the implications on power, things like that. And I think a lot has been written about it. But the problem, I think, is that most of these blog posts, they're written by a statistician, and I can relate to wanting to really focus on the statistical issues that arise, right? In particular, things like power. But in practice, it's not only the statistics that matters. There's a variety of dimensions that I think are important to take into account. And if you just hone in on statistical power, first of all, it's hard to compare the methods apples to oranges just because they work slightly differently. And so it's hard to create a fair comparison. And so I thought it would be good to work on making that argument and trying to more holistically write down kind of the trade offs you're making by choosing one methodology versus another. And then also, I come to the realization over my time here at Eppo that there's not really one best method. Some people prefer to be Bayesian. Other people have good reasons to use the sequential methodology, and yet others they just want to use the classical fixed sample test. And each of them are right in their own ways, and that's totally fine. So it's just good to try to take a step back and figure out why do people pick different methods? What are the reasons behind it? And write that down for people who want to make that decision and want to think a little bit more carefully about it.
Right, there's almost a concept of culture fit for figuring out which method is best.
Exactly. Yeah. I think culture actually matters quite a bit on deciding what method fits well. If you're early on in your experimentation journey, you're in a very different stage and you might make very different trade offs than when you've been doing this for a long time. And it might also just be what are people used to, right? And if they're used to something, there's a cost to changing that. And is it worth it to change that? Maybe not.
So let's talk a little bit about each of the factors that we put in these spider graphs to visually compare the stats methods. So the first one we ranked on was obviously power, but we're using quite a broad definition of power and very much not a traditional one. You want to talk about that a little bit?
Yeah, so formally, power basically measures. Suppose you run an experiment, and this is really a frequentist phenomenon or notion, so it doesn't really apply or carries over that well to Bayesian statistics, but basically says if there is an effect, and I repeat my experiment over and over, how likely am I actually to pick up on this, right? So it's kind of the sensitivity of your experiment. Comparing sequential tests with fixed tests is a little bit difficult when it comes to power. It really depends on how do you set up your experiment to compare these. So instead, we want to take a step back and just say one way to think about it that you can do is you run an experiment for a fixed amount of time. And at the end, you might generate some confidence intervals or credible intervals. How wide are those, right? And that kind of gives you some sense of sensitivity. It might not formally be the same as a notion of power, but it kind of captures the same essence. And that feels like an intuitive notion that kind of applies to all these methods. If I run an experiment for a month or 2 weeks, what's my sensitivity at the end?
And that leads us straight to the second factor, which was flexibility. Well, a method is able to adapt on the fly if your observed effect size is different from the one you expected or set as a minimum detectable effect. Simplicity was another factor that we're considering here. How comprehensible are the
Mhm.
underlying concepts for a general audience? I think that's a very popular argument for Bayesian methodology, is that it is supposedly more intuitive for a general audience to understand what the test is actually trying to infer. But there is also some considerations and simplicity about setting up the test. Does it require a lot of forethought, or can you just kind of turn it on? Anything we should say about simplicity, especially as it relates to the different flavors of sequential tests?
Yeah, of course. I think, first of all, like all these dimensions, there's some level of subjectivity. And with simplicity, what's simple to some or intuitive to some might not be intuitive to others. So it depends a little bit, your background and your level of expertise. But yes, I mean, Bayesian statistics is kind of has this claim to being intuitive. You could challenge that a little bit because setting up a prior might not be that intuitive to folks, right? Doing Bayesian statistics well might not be as simple as it at first seems. I think it's interesting to think about sequential testing. Again, you could argue how simple this really is. I think on one hand, the fully sequential methods, I would argue, are fairly simple in the way that you can set up your test, you can look at the results, and it's hard to go wrong. They're fairly conservative, and you can peak, for example, and your confidence intervals are automatically adjusted for that. So, in some sense, you're avoiding that trap. Maybe understanding the precise guarantee that this confidence interval contains the truth, the true effect, assuming no non-stationarity and stuff 95% of the time across the entire time frame might not be super simple to wrap your head around, but maybe that technical detail isn't really necessarily to fully grasp to make good decisions using this. We found that group sequential testing is a little bit less intuitive just because there's a lot of choices you have to make that might seem a little bit harder, like how often should you peak and how does this matter? But in general, I think still it's kind of easy to explain.
Yeah. Well, since you mentioned non-stationarity, maybe we should jump to robustness. I think that's definitely an important one. Describe it for those of us who are not statisticians. What are we talking about when we're comparing robustness of these tests?
Yeah, I think in general, across all of statistics, maybe mathematics more generally, is you're applying methods, and these methods rely on assumptions that we make about the world or the problem. And, in theory, we can make really nice assumptions that make the math work out great. But in practice, often some of these assumptions might not hold, all right? You might worry about them. And ideally, a method doesn't completely break down when assumptions that might not hold in practice. And so it's interesting to see for each of these methods, they make different kinds of assumptions. What happens when some of the assumptions you would commonly make, but would also commonly break in practice? What happens, right? And so the things we're thinking about here, there is non-stationarity, right? In many experiments, the effects early on in an experiment might be especially strong or especially weak. There might be novelty effects. People might not understand the treatment. It might take them some time to wrap their head around how you've changed application and how they should change their behavior, right? So you might expect the treatment initially to look bad. And as your users in the treatment group get used to it, they get to see the benefit. Or maybe they get very excited about this new feature, but it's not that useful. So initially you see a lot of usage, but it quickly dies down. So these type of effects we see very often. And then obviously the sequential methods that look over time are a little bit sensitive to that, right? If you run a fixed test and you run it for a month and you look at the end of the month, you don't care what happened in that first week. You're just looking at the full picture. But other ways that I think are a little bit more subtle, and the folks from Spotify wrote a great blog post about this, is that often we make this assumption that we observe an outcome on a unit that we analyze, users, for example, only once. But in many cases, and not for everyone, but most folks continuously observe outcomes of users. So, for example, you might have a revenue metric, and over the course of an experiment, a user might make purchases, right? So their revenue on day zero of the experiment is zero. Then on day one, they buy something for $10. Now the revenue that we consider is $10, right? And then day three, they buy something for $20. Now their overall revenue is $30. So we update the metric for this user over time. And there's an assumption underlying all of these sequential methods that this is not happening. And the folks at Spotify show that, and in particular, they look at group sequential methods, that they're quite sensitive to this because they really rely on the assumption that across time, these units are independent. And so that's another kind of robustness thing that we looked at. But those are the kind of problems that we're thinking about.
Yeah, the folks at Spotify coined it as the peaking problem 2.0. Yeah.
Right.
Okay, and then the last factor that we evaluated was implementation, and I think this is something that you are uniquely posited to give a perspective on because of your role as statistics engineer at Eppo. You are not just a statistician; you are also responsible for taking the statistics and implementing them in code in the product, and there is some degree of consideration around how easy is that to do. Are there commonly available packages, or is a method very computationally intensive? How wide of a range are we talking about when we're talking about a t-test versus Bayesian versus these different sequential methods? Like, how hard can it get to implement?
Yeah, that's a great question. I think the range is actually pretty wide. And
Okay.
I think this is also the easiest dimension to evaluate these methods on because clearly, kind of the classical t test is basically a one liner, right? You can easily find that on Wikipedia. It's very simple to implement. And then fully sequential methods, they sound complicated to implement because there's a lot of math behind it. But in the end, it's a slightly longer one liner. And I know because I've implemented it. So it's not that different to do versus a t test. Then Bayesian statistics gets a little bit more tricky because it really depends on how advanced you want your Bayesian statistics to be. For example, if you model your data with a standard normal prior and you model your outcome as a normal distribution as well, and you have a conjugate pair and this update, you know your posterior is again normal, it's not that complicated to implement, right? It's definitely a little bit more logic. You got to get the maths right. So it's definitely a little bit more tedious to implement, but that simple setting is easy to do. But if you want to do more complicated and realistic things with a Bayesian approach, it gets tricky far faster. So, for example, if you want your prior to capture that experiments often have heavy tailed outcomes, like very often there's no effect and sometimes there's very big effect, and researchers across companies have noticed that this is often the case. There's a famous paper from the folks at Microsoft that talks about how they see heavy tails, and so if you want to take that into account, there's no closed form solutions anymore. You need to figure out either how to integrate some distribution or run MCMC algorithms. So it can get complicated quickly if you stray away from kind of the easy path. And then group sequential, I think, is interesting too, because it feels like, unlike all the other methods, there's far less publicly available material that's just open. So if you use R, there's some packages that let you do it. But even in Python, it's relatively difficult to find something. The folks at Spotify released an open source package that kind of ports an R implementation to Python, but it's definitely far more finicky to implement. So
Yeah.
I consider that to be one of the harder ones, also just because there's much less public information on how to do it well. So that's one factor that comes into mind.
All right. So let's actually dive in and go test by test. We've already covered a lot just in the course
Mhm.
of conversation, but let's do a quick synopsis of each method and sort of where we see people reaching for them, or where we might recommend it, what situations, what context. And we can start with the classical t-test. And classical for a reason, right? Very efficient on power, very robust, very easy to implement. Like you said, it's a one liner. But of course, the trade off is that we're assuming organizationally we'll have some discipline around planning the test in advance and not peaking. And obviously, that's very hard in practice for a
Mhm.
lot of businesses and a lot of teams. And on the simplicity front, I think one of the obvious criticisms is that most people don't really understand what it is that a p-value is describing. It's often hard to grasp frequentist concepts. So I guess, what kinds of teams do you see reaching for t-tests, or using them primarily? Who would you recommend a t-test to?
Yeah, it's a perfect question based on our experience at Eppo and more generally. There's kind of three stages of experimentation almost, and it might be good to look at the t test in that, right? Like if you're a very small company just getting started with experimentation, you might have a data scientist or two that are trained in statistics. They might run the first few tests. They understand this t test very well, and it's a very controlled environment. And because you're very early, you might not have a lot of data. So what you really care about is when you're in this really data sparse case, right? You want to see, well, we can run this test for maybe a month, right? Maybe that's how long it takes to gather enough data. And at the end of the month, I want to get the tightest confidence interval possible. And that's kind of the only option I have, is to run a t-test. And because you have a trained data scientist do that, I think it's a great use case. And so for very first experiments, it's also simple to get started, right? Simple to implement. A t-test is great. But then when you start running more tests and train an organization to build a culture of experimentation, and you want to scale this to product teams, self-serving experiments, right? Now you get into this scenario where you might want to avoid having to explain p-values or having people grasp all the intricacies, doing a power analysis the right way, understanding what kind of treatment effects to look for. So I think in kind of this second stage where you're not really super sparse in your sample, you have enough sample size, but you're not completely like at Facebook scale, then you might think that maybe the t-test is less applicable compared to something like a sequential test that is a little bit more flexible, or maybe a Bayesian approach, which is maybe a little bit more intuitive and is easier to scale, especially toward folks who didn't like statistics 101. But then if you look at the really large companies like Facebook, Microsoft, LinkedIn, others that have a lot of data, you see that often they use just simply the t-test again. And it's good to understand why. And I think one of the reasons is they have so much data that basically they can end an experiment if they want to in a day, or maybe even a couple of hours, or maybe even a couple of minutes if they test something that just touches upon a lot of users. The problem is if you work on, say, Instagram, you don't want to run an experiment for a couple of minutes or a couple of hours, right? Because you realize there's strong novelty effects and who shows up is complicated and it changed over time. So when you're at a really large scale, what you're doing is you don't run your tests on 100% of the population anymore. You're saying basically, I know there's strong weekly effects, so I'm going to run my test for at least a week, right? Or 2 weeks. Now, I can run it on all my users, but I get way more users than I need for this experiment. So I'm going to figure out, I know I have to run this experiment for a week. If I run it on 5% of my users, I get enough power to run it for a week. So when you get to that stage where you're no longer deciding how long to run my experiment for, but rather that is fixed and you're deciding what fraction of my users do I experiment on for a set amount of time, then you see the t-test becoming powerful again and used a lot. So that's kind of the final stage of experimentation. And then another point I think that's important to make is that there's several reasons why you might want to run an experiment. One of those reasons is you want to make a decision. You have this product launch and you want to decide, should we roll this out or not, right? And in that case, you might care about just making that decision as quickly as possible. I think the t-test isn't flexible enough to really help you make that decision as quickly as possible. But other times, you're just trying to understand your business better and you're running an experiment to just gain a better intuition. And in that case, what you care about is getting tight confidence intervals at the end, really understanding this effect. And in that case, t-test again is great. So I think another way to think about the value of a t-test is really when you're looking to maximize the knowledge you get from an experiment rather than trying to optimize the speed to make a decision.
So let's pivot then to sequential tests,
Mhm.
where we introduce this wonderful world of flexibility. So I'll give my simplified non-statistician description. Essentially, they enable us to potentially conclude an experiment earlier than we would otherwise if our observed effect size is large, positive or negative, just giving us some boundaries to say, okay, if we're observing a really large effect at a certain time point, that may be compelling enough evidence to conclude the experiment. Is that a fair layman's description of what's going
I
on?
think, yeah, I think that's really fair. Often people put the emphasis on rolling out winners early, but I
Hmm.
think an equally vital part of this, right, is that sometimes things really don't work out and you want to stop it as early as possible. So really two sides, and obviously it works on both sides. So I like that you highlighted both of them.
Let's start with a fully sequential test because maybe that's the easiest to grok for people. We're doing away with a lot of the need for pre-experiment planning. We're no longer worried about choosing a minimum detectable effect or fixing a duration in advance. We're just going to launch the experiment and assess the data we're collecting over time. In a way, it's the ultimate option for flexibility, but I think the point I hear in conversation often is that it comes at a notable cost to power. I think you have a slightly different way of looking at that or evaluating it. So I'm curious to hear your defense of fully sequential tests.
Yeah, it's a great question. Before you go there, I wanted to touch upon something you said. You started with like, oh, you can basically dive in headfirst with a test and you don't have to do that work. And I just wanted to add that, yes, the test itself is not as reliant on doing that work. But there's probably still value in understanding roughly, right? If
Mm.
the effect is this big, roughly how long do I expect this experiment to take? Because you can say like this sequential method, it will adapt. But if you set up an experiment where it would take half a year or maybe 3 years to detect a reasonable effect. This sequential test might adapt to that, but you might want to know that ahead of time and maybe adjust your test to avoid waiting for 6 months up to 3 years, right? The good thing about sequential tests is that it's not so sensitive to that early analysis, and you can certainly get away with not doing it, but it's probably good practice to do it still.
Yeah. How
Um,
to do that, I'm sure, could be a whole
about that.
separate conversation.
Yeah, I mean, and the other question you asked was about the concern that sequential tests take a lot longer. And that's probably also worth a longer conversation to really dive into. But I'll try to kind of summarize my thoughts. There's two different ways to look at it. And I think one of the ways is just like, let's look at the width of the confidence intervals, especially at the end. And you'll notice that when you run a sequential test, your confidence intervals will be almost twice as wide than the t test. Not quite, but pretty close to twice as wide, right?
Yeah.
And naively, that would mean that your test takes 4 times as long to run, right? Because there's this quadratic relationship here. So if your confidence interval is twice as wide, it takes 2 times 2 is about 4 times as long to get the same level of specificity. But that's really an unfair comparison because it completely ignores the benefits of the sequential test, which is that you don't have to wait till the end and that you can stop a test sooner. And so, one way to think about this is why were sequential tests invented or why were they popularized? It was to avoid the peaking problem. And what is the peaking problem? Basically says over the course of an experiment, your treatment at some point is going to get lucky and look better than it actually is. And at some point is going to look worse than it actually is. It fluctuates. Sometimes it looks better, sometimes it looks worse, and sometimes it might look a lot better, right? And that's when if you peak, you hit a problem. You don't take this variability into account and you claim early victory when it comes to a t-test and you break your type 1 error guarantee. And sequential tests fix this by saying, okay, we take this variability into account. And so that's where the sequential methods get back a bunch of their power because they get the flexibility to stop early when the test actually looks better than it is. And so that's why comparing the confidence intervals at the end is a bit unfair. And so the real way to think about what happens is not so much a trade off in power, but more that sequential tests tend to stop when the point estimate of your effect is exaggerated. It's either too good to be true or too bad to be true. And that's kind of the opposite from a fixed sample test. It allows you to make a decision, but it's not so great for knowledge, right? And this confidence interval, in the end, a sequential method, all it does is create a confidence interval. It does not change the point estimate whatsoever. The problem is at the point that you stop, this point estimate might look extra good. The sequential method, it's only concerned about giving you a confidence interval, and this confidence interval is correct. It doesn't really care that this point estimate is likely to be a bit biased or quite a bit biased. So that's the real kind of downside of sequential testing, and especially if you're looking after understanding the impact of a certain treatment. It's not so great to get precise knowledge because it tends to stop at a time where your point estimate doesn't really reflect the true underlying effect.
Yeah.
Note that the true underlying effect is likely still contained in your confidence interval. It's just
Sure.
not at this point estimate.
So, in a fully sequential test, we're hypothetically enabling continuous peaking. Peak at any moment as many times as you like, and the results will be valid. A group sequential test, in contrast, we are introducing some discipline again. We're planning a number of peaks, a cadence, and a number of peaks that we're willing to do. The difference is on paper, a group sequential test is more optimal for power. Obviously, we're giving away some of our flexibility. But like you mentioned much earlier in the conversation, there is maybe a new concern around robustness introduced with that peaking problem 2.0.
Yes. So I think basically group sequential tests get you more power because of two reasons. The first reason is that you get to limit the amount of peaks. And in particular, at some point, you say, I won't look at this experiment anymore. It has a clear end date. The fully sequential methods basically allow you to run this experiment forever, right? You get to peak till the end of time. And so we still have to make sure that if you were to run this experiment till the end of time, we still generate correct confidence intervals. That's a very strong guarantee. And that means that it has to be conservative. So the first thing that's group sequential tests do is they put a cutoff at the end. So at some point, they don't have to care about making errors anymore. And so that helps, less conservative that way. Also, it limits the amount of peaks. By limiting the amount of peaks, the fewer times you look, the fewer opportunities you have to make mistakes. So you can be a little bit more aggressive in how tight your confidence intervals are. So in that sense, both fixing the end time as well as in between having a few number of peaks allows you to be far more aggressive, leading to tighter confidence intervals or higher power. That's one. I think the other one is that group sequential tests really are, in some sense, the analysis of what the confidence intervals look like. That analysis is pretty tight, and that helps. In fully sequential methods, there is some slack in the mathematical bounds that we create. And, people are working on getting tighter bounds, right? But there is just some extra slack that comes from the mathematics is complicated. We have to take some shortcuts to get to some tractable results. And in group sequential methods, we're able to stay closer to the real effect. But the downside of that is to do that, you make some assumptions. And those assumptions that we talked about earlier around seeing an observation or getting a single observation per user and not an observation that changes over time is, for example, one assumption that often breaks in practice. And so that's where this peaking problem 2.0 that Spotify points out comes into play. And one of the ways, I think, in which group sequential test is a little bit less robust than fully sequential testing.
Then we talk about one other flavor of sequential tests in the post that I think is somewhat unique to what we do at Eppo, at least in a commercial experimentation platform. I haven't heard of anyone doing something similar, but describe this hybrid sequential concept to us.
Yeah, that's a great point. And in some sense, the hybrid sequential test is a really basic and natural extension of the tests we already talked about. And so we just spoke about how the fully sequential test has to make sure that we are able to run this experiment till the end of time and generate correct results. And that leads to conservatism and wide confidence intervals at the end of the experiment. And I totally resonate with people that do not want wide confidence intervals and when they run an experiment for a fixed amount of time, right? You might have this case where you run this experiment for a month, and no matter what happens at that point, you have to stop the experiment. Maybe there's no effect, or maybe the effect is small. You want to have a confidence interval that is as tight as possible at that point in time. So I get that problem with sequential tests. But on the other hand, you also really want to stop experiments early when they look really good or really bad, right? If there's a bug. So people kind of want the best of both worlds, right? They want to be able to stop and test early when there's a big effect in either direction. But if there's not a big effect in either direction, they still want a lot of power at the end. So basically, what that looks like is I want to run a sequential test until the end of my experiment, and then I want to do a t-test. Well, we know we cannot do that, right? But we can almost do that. And so that's what this hybrid sequential test is doing, is basically saying, let's run this sequential test while the experiment is running and switch to the t-test at the very end. But to make the statistics work, we have to be slightly more conservative. And so how we do that, basically you have this error budget of alpha. When you run a simple t-test, you say, with some probability alpha, I'm going to be wrong and I'm going to claim there is an effect even if there isn't. And so instead of using alpha, we use alpha over 2 for both. So each of them get kind of half of the error budget. And that way we get best of both worlds. So we basically get to run the sequential test while the experiment is running, get the frequentist t-test at the very end. And we control the statistical type 1 error that we want to control. So in that sense, it is a great way to interpolate between the two and get the best of both worlds. So I think it's a great trade-off to make. And in general, it is very simple. It's almost a hack, but I think it is, on the other hand, quite attractive for many folks. And so worth considering.
So to bring it back to who might want to reach for sequential tests, it seems like group sequential tests are very popular with teams that are pretty experienced experimenters and have a good grasp on statistics. But we often recommend fully sequential tests as a good default starting place, especially for teams who are new to experimentation and maybe don't have a lot of background in statistics. Why is that?
Yeah, so I think early on in this conversation, right, we said that there is no single best method. And that's true. But the thing that I think is nice about sequential methods is at least you can't really go wrong with it. You can't make mistakes. So in some sense, it's kind of the safe choice. And then if it's not appropriate, then people can think more deeply about what is most appropriate to them and switch to the method that works best in their situation.
Yeah, I'll also say in my experience, because I've worked with many companies and teams on experimentation, the need for flexibility and to enable peaking is quite common. It's very rare, I think, that a company that's new to and I really mean a company that's new to experimentation, not just the data team, but for the people surrounding the experimentation effort who are curious about results and want to evaluate what's going on. Very rare for them to understand why peaking is a problem and to have the patience and discipline to not peak. So especially early in the culture building process, enabling that with a fully sequential method seems pretty imperative.
Yeah, and in some sense, when you run an experiment, it's like everyone is going to want to peek and look at the results as they come in. I remember when I was running experiments at Stitch Fix, obviously I'm going to open that dashboard every day and look what the results were. We weren't doing sequential tests and we were realizing we get to look at these point estimates and we are not going to make a decision based on this, right? But obviously we're tracking this and we'd get emails from leaders that would look into this and they say, oh, it's looking good, right? Like fingers crossed that this maintains, that we see this positive result at the end. It's fine to look at experiments early, even if you have this t-test, you just can't make any decisions, but that is very hard to explain to people. And so it can just be nicer to have this peaking kind of this sequential testing to build in and not kind of get people's hopes up too early.
So let's wrap this up. It's turned into a full podcast episode here, but I'm always so appreciative of your insight and perspective and ability to explain all this stuff, I think, in a very reasoned and approachable way. So let's bring it home with the most apples to oranges comparison of them all and talk a little bit about Bayesian analysis and epistemology. And I think rightfully you point out in the post that people who prefer Bayesian, it's largely a matter of tastes. This one becomes less about the practical trade-offs between these factors and more of a philosophical difference. But talk to us a little bit to whatever extent you can the compare and contrasts with the frequentist methods.
Yeah, obviously now we're getting into dangerous territory here, right?
We're gonna get canceled.
I think the first thing that is just very clear, some people prefer Bayesian analysis, some people prefer frequentist analysis, and that's totally fine. If there was one clearly better, the debate would have been settled a long time ago. And so clearly there is something to be said for both of these methods. But I think, to be honest, it's good to understand the other side. And even if you're a frequentist, let's look at the benefits that a Bayesian analysis can give, and vice versa. If you're Bayesian, let take off the rose tinted glasses and look at what the benefits are of a frequentist analysis, and it might make you appreciate both methodology a bit more. Think in practice, it turns out most experimentation teams lean frequentist. And sometimes I think that's a little bit of a shame because I think there's some clear benefits to a Bayesian analysis that where teams that solely focus on a frequentist analysis kind of struggle with. In particular, what is nice is it's the results are more intuitive to explain to stakeholders. Like you can say something about, and we have to caveat this, and we'll talk about the caveats. But if you can say something about the probability that you beat control is 75%, that is intuitive to understand for a PM. Now, whether this statement is correct, right? That's the hard part about Bayesian statistics. But there's other benefits. In some sense, it takes care of the peaking problem for you without really having to worry about it too much. While frequentist academics have had to spend a lot of blood, sweat, and tears to solve this problem. And the same is it happens with multiple testing correction. Like for frequentists, this is a problem. For Bayesians, there's some automatic kind of dampening of effects. There's not really an issue of winner's curse. And so that's all very convenient and great advantages of Bayesian, but it rests on a fundamental assumption. And that is that you're prior, that you believe it, right? And that's tough because that's a leap of faith that you have to make. If you run a lot of experiments, you might have a really good sense of kind of the type of effects you can expect. You can encode that in a prior. It's kind of the empirical Bayes type of way. It's bringing some frequentism to Bayesian statistics, and you can really feel really good about your prior, and then your Bayesian results seem to me to be very believable. But in other cases, if you're taking a big guess on your prior and you're wrong, then all these guarantees go out of the window. Then you do have the peaking problem. Then your claim that probability that treatment beats control 75% is bogus. You don't get enough shrinkage to correct for looking at a lot of metrics. So the nice thing about Bayesian statistics, it solves a lot of problems that data teams struggle with if only you get this prior right.
Just to zoom in on that a little bit more, because I know we will get someone commenting about a claim that a Bayesian approach helps solve for the peaking problem. It is when you are using a very opinionated prior that benefit comes to light. Yeah.
Right. Yes. If you have an uninformative prior, basically your Bayesian analysis is the same as a frequentist analysis. And
But
obviously,
without
if it's the
guardrails.
same, you have the same problems. And so here's your peaking problem. And the benefit of Bayesian statistics is it helps you avoid that a little bit, because if you don't have enough data, you just go back to your prior. And again, if your prior is very conservative and says, I strongly believe that there's no effect, then unless you have enough data to convince you otherwise, you're not going to claim that there's an effect. So that's how you avoid that risk. And then I think so early on in the conversation, we talked about how this t-test is good when you're small, maybe at a medium scale, you want to consider sequential tests. And then when you're at a really large scale, you want to switch back to a t-test, right? I think the Bayesian paradigm, the nice thing is you can use that throughout the lifetime. In general, it works well. It makes sense across a wide variety of settings. I think Bayesian statistics is a solid choice, no matter what.
We've compared them all. I think we compared them very holistically. I think we've solved the statistics wars. Yeah.
I doubt it.
I
A
don't
bit
know.
of
I think
heated.
this is it. I think we did it. I think we'll just direct folks to this conversation, and no one will ever fight about what stats method to choose
I
again.
mean, the statistics wars provide a lot of entertainment, so let's hope we didn't
It's
end
true.
them.
All right. Well, thank you for walking us through all this and taking the time to have this conversation. I hope it's super helpful to folks. Obviously, everything is referenceable in the blog post on the Eppo site, frequentist versus Bayesian versus sequential methods, and comparing them. And if folks have questions, you should always reach out to Sven or myself on LinkedIn, or the Eppo page on LinkedIn, or in the comment section here. And I'm sure there will be no shortage of good conversation on these topics.
And that's good. I think a lot of my thinking has been shaped by my experience at Eppo over the last 2 years. And I imagine that over the next couple of years, that thinking will evolve, and it will evolve because of the discussions we'll have based on people's feedback. So we should keep the conversation going and learn from each other.
All right. Well, thank you very much, Sven. We'll talk to you soon. And thanks everyone else for listening.
All right. Cheers.